Okay, so we're going to look for some different examples of some different growth and decay models in section 6.8. So we've already seen how money can grow exponentially. We've seen how it can grow at certain time periods. We've seen how it can do continuously. So in section 6.8, we're going to look at a lot of things that grow continuously, both grow and decay continuously, actually. So the first law we're going to look at is what's called the law of uninhibited growth. So the law of uninhibited growth or decay is simply going to be A of t, so some amount for some given time, is going to be equal to A of 0 e to the kt. So we have to know what all these things are. We know what e is. E is our special number, our base of our natural logarithm. A sub 0, we call it A naught sometimes, is the original amount. And k is just some constant, so it's not 0, so k is just some number. Now the trick will be if that number is positive, then these things will grow, and if it's negative, these things will decay. Okay, our second kind of thing is just kind of an offshoot of this. This is kind of talking about uninhibited growth of cells. So since we're talking about cells growing, we're talking about some amount growing, then this is going to just make our k positive. So the way we'll write this is we'll write it n sub 0 e to the kt, and you can see here k is positive, and that's going to make these things grow. And again, n is going to be the initial number of cells, so how many cells you start with, and then k is going to be some kind of positive constant. So as these things start growing, you get more and more and more cells, and these things basically grow uninhibited. So you can think of cells or bacteria or things like that just keep growing and growing and growing and growing. So our first example here kind of is an example of this. So it says a colony of bacteria grows according to the uninhibited law of uninhibited growth according to the function n of t equals 100 e to the 0.045 t, where n is measured in grams and t is measured in days. And that's very important that we know t is days. When our money, we did everything in years, and n is going to be in grams. So this is following that general formula. We said that this is going to be n sub 0 e to the kt. So we can see our n sub 0 in this case is 100, and our k is 0.045. So to determine the initial amount of bacteria, well, the initial amount of cells is always given by n0. So the initial amount is this n0, which is the number in front of e. So in this case, it's 100, and it would be grams. So this bacteria starts at 100 grams, and then it gets larger and larger and larger and larger. Now, for uninhibited cell growth, we can talk about the growth rate. Growth rate is simply going to be, in our case, k. So k is 0.045, which as a percentage is 4.5%. So that's the growth rate. Now, all the rest of these problems really just kind of take into account what is t and what is n for certain values. So part C says, what is the population after 5 days? Let's say if t is 5, then what is n of 5? So we're trying to find the number of cells after 5 days. Well, since we know that n of t is equal to 100 e to the 0.045 t, when I'm looking for n of 5, all I'm going to do is plug in 5 for t. Now, these are all just numbers, 100 e to the 0.045 times 5. Go ahead, pause the video, make sure you put this in your calculator, make sure you get the same thing I get. So I went ahead and I got n of 5 to be 125.23. And since this is the number, this would be in units of grams. Okay, so that's one where you just plug in the time. That's a pretty easy example. The second kind of example we can have is we want to know how long it takes for something to occur. So in this case, it says how long will it take the population to reach 140 grams. So we want to know how long until the number is 140 grams. So it starts at 100, how long until it gets to 140? Well, if I start with my formula over here on the right, N of t equals 100 e to the kt. Oops, we know what k is. K is 0.045, so let's put that in there. So now it says, all right, if the number is 140, can we solve for how long that takes? And what we get is just a pretty simple exponential equation. So just like always, I'll start by dividing both sides to get the base by itself. So 140 divided by 100 is 1.4 equals e to the 0.045t. And now I have it in exponential form. I'll just switch it to log form. So this is log base e, which is the natural log. So it's natural log of 1.4 equals 0.045t. And so I'll simply divide out by 0.045. So I do the natural log of 1.4 divided by 0.045. I get 7.48. And since this is the time, this is going to be in days. So it takes about 7.5 days to go from 100 grams of cells to 140 grams of cells. Okay, let's look at the last problem. It says, what is the doubling time for the population? So doubling time, we want to know how long it takes for the initial amount to double. So it's a very similar problem to the problem above, because what we're trying to figure out is we're trying to figure out when the number of bacteria will go from 100 to 200. So we'll say we're trying to figure out when is N of t equal to 200 grams. So if we plug that into our equation, we get 200 equals 100 e to the 0.045 t. Of course, still divide by 100. 200 divided by 100 is 2 equals e to the 0.045 t. So very similar to the one above, we'll switch it to log form. So this would be natural log of 2 equals 0.0545 t, pardon me. So t is going to be the natural log of 2 divided by 0.045. So the natural log of 2 divided by 0.045 is going to give me 15.4. And since this is time, this is going to be in days. So to double my initial amount, it's going to take about 15 days. Okay, let's look at a second problem here. Now this one's a little different. It says, all right, well, a colony of bacteria increases according to the law of uninhibited growth. According to the formula, N is the number of bacteria, T is the time, and the number of bacteria is the initial amount times e to the kt. Now in this problem it says if 10,000 bacteria are initially present and the number doubles in 5 hours, how many bacteria will there be in 24 hours? Now the problem with this one, which wasn't really an issue in our previous problem, is we don't know what K is. So the big problem here is we have to figure out first, what is our value of K? Now if we think about our problem, we have N of T equal N sub 0 e to the kt. That's our general formula. Now, it says there are 10,000 bacteria, 10,000 grams, or I'm sorry, 10,000 bacteria in this problem, 10,000 bacteria initially, e to the k. We still don't know k, but we do know that in 5 days it doubles. So for time, I can actually plug in 5, and in 5 days that should equal 20,000, because that's double our initial amount. So now we have an equation with one unknown, we can actually find what K is. So if I divide by 10,000, I get 2. So 2 equals E, and I'm just going to write it as 5K just to make it look a little better. So if I convert that to log form, I'm going to get the natural log of 2 equals 5K. So K is going to be the natural log of 2 over 5. So that is our actual value for K. So if we put that in a calculator, figure out that out, K is going to be 0.1386. And that's not very surprising because we knew it should be positive because it is growing. So now we really haven't answered the question. We just now know our equation. We know now the number of bacteria starts at 10,000 E, but now we know what K is. So if I look at this formula up here, now I solved that K was 0.1386 times T. So now I can do whatever I want, and this problem says how many bacteria will there be in 24 hours? So really I'm trying to figure out what is N of 24. What happens when I plug in 24? So that's going to be 10,000 E to the 0.1386 times 24. So if I've done this correctly, I'm going to get 278379.5 bacteria. So it grows a lot. It grows from 10,000 to 278,000 in 24 hours. But it doubles in 5 hours, so it keeps doubling and doubling and doubling and doubling and has that growth. The second part of this problem says, okay, how long until there are 500,000 bacteria? Well, same problem as above, so I'll just plug in 500,000 for my amount. So essentially we're trying to figure out how long for 500,000 or 10,000 to grow to 500,000. Now I know a couple things. I know it's bigger than 24 hours because in 24 hours we're only at 278,000. So we take 500,000 equals to e to the 0.1386 t. So we'll divide by 10,000. So if I divide 500,000 by 10,000, I get 50. So it's 50 e to the 1.386 t. I'll change this to logarithmic form, which is going to be the natural log of 50 equals 0.1386 t. And I'll divide both sides by 0.1386. So t is going to equal 29.04. And the unit in this case, remember, is hours. So for all these problems, the big thing, find your equation and then use your equation for whatever the problem's asking for. Okay, so our next problem is going to talk about one that's decay. So we're going to talk about radioactive decay, something going down. And we said if something's going to go down, then that K value better be negative. So the amount of radioactive material present at time t is given by this formula. We call it almost exact same formula, A0 e to the kt, but in this case K is less than 0. Since that K is less than 0, this is going to be decaying. And so A0 is the initial amount, just like always, it's how much you start with. And K is going to be, in this case, a negative number that represents the rate of decay. Now, one term we'll use a lot in this radioactive decay section is the term half-life. Half-life is simply the time required for half of the radioactive substance to decay. So if you have 10 grams of radioactive material, how long it takes to go down to 5 grams would be your half-life. So let's look at an example of this. So we have a problem where the equation is given. It says iodine 131 is a radioactive material and decays according to the function A of t equals A sub 0 e to the negative, and there's your negative, 0.087 t, where A0 is the initial amount present and A is the amount time and t is the time in days. So A is the initial amount. So, in this case, what is our initial amount? It says it is 200 grams. Okay. So, right away, we know our formula. Since we know our initial amount is 200 grams, it's going to be 200 e to the negative 0.087 t. So, this is the formula I'm basically going to use for this whole problem. So, the first thing says, what is the decay rate of iodine 131? Well, we know the rate of decay is just K. We said that up above. So this is just 0.087. So it's 8.7% is our rate of decay. So number B says, how much iodine 131 is left after 5 days? So that would be a T of 5. So really we're trying to find what is A of 5. So A of 5 is going to be 200 e to the negative 0.087 times 5. And the good news is that's all stuff I can just plug in my calculator. So make sure you get the same thing I get. I get 129.45. In this case, since our initial amount of radioactive material is in grams, this should also be in grams. So this thing is decaying pretty quickly because it went from 200 grams to 129 grams in only 5 days. Some things that we do radioactive decay on can take hundreds of years, thousands of years. It just depends what your material is. Okay, our last one says, when will 100 grams of iodine be left? So again, just like the growth problems, we're essentially saying in this case, when was our amount going to be 100 grams? So if I plug that into the equation, we have 100 equals 200 e to the negative 0.087 t. So I'll divide by 200. 100 divided by 200 is 1/2 equals e to the negative 0.087 t. I'll take the natural log of both sides, or switch it to log form, whatever you want to think of it as. So we get the log of 1/2 equals negative 0.087 t. So of course t is going to equal the natural log of 1/2 divided by negative 0.087. And don't fret about the negative 0.87 because the top is going to be negative as well. The natural log of 1/2 is negative as well. So when you divide those two things, you get a positive number, 7.97. And in this case, since it's time, this is in days. Our previous example was on hours. This one's in days. Everyone can be different depending how it's growing and how it's decaying. So let's look at one more example. This is just kind of an interesting little problem. So this is kind of a fact that living things contain two types of carbon, carbon-12 and carbon-14. So when a person dies, the amount of carbon-12 will stay constant. It doesn't go anywhere. But the carbon-14 will decay. Carbon-14 is said to have a half-life of 5,730 years. So it takes a long, long time for the amount of carbon-14 to decay. But that's really easy to be able to calculate how long ago when an organism died, or how old it is, or how long it's been at a certain place. Okay? So we'll look at an example of that. So this says, traces of burnt wood along an ancient stone tool in an archaeological dig in Chile were found to contain about, and this is an important piece of information, 1.67% of the original amount of carbon-14. If the half-life of carbon-14 is 5,730 years, approximately when was the tree cut and burned? So when did this tree die, essentially? So we know that our radioactive decay formula is still the same as we talked about. It's A of T equals A0 e to the KT. But this is kind of a tricky one because we don't know how much carbon was initially, right? So we don't know what A0 is, and we also don't know what K is. So we're going to have to do this one a little different. The key in this one is actually found in this amount of half-life. So it says the half-life is 5,730 years. So that means when my time has passed, when my time is 5,730 years, then my amount is going to be half of what I started with. Now I don't know how much I started with. I just know it's some A0. So half of what I started with is just half of A0. So the first thing I'm going to do is I'm going to find K. So what I know is I know half of A0, half of what I started with, and I don't really know what I started with, so I'm just going to say half of the initial is equal to the initial e to the k, but I know to get to that half-life it takes 5,730 years. Now it looks like we have too many variables here, but if you notice you have an A0 on both sides. So if I divide by A0, everything cancels out. So I just simply have 1/2 equals e to the 5730k, if I just switch those around like I've done earlier. So this is actually going to allow me to find k. Because now if I take this value and say, all right, this is going to be the natural log of 1/2 equal to 5,730k. Divide out, k is going to be the natural log of 1/2 divided by 5730. So whatever that is, put it in my calculator, I get k. It better be negative, which it is, 0.000121. So it's a really small k because this is an extremely slow decay rate. But now I have my equation. So I know the amount of carbon-14 is the initial amount of carbon-14, e to the negative 0.000121 t. Now I'm not done yet, because now it says, so now I just know the equation. Now I have to figure out how long would it take for the carbon-14 to go to a full amount to 1.67% of the original amount. It's a very similar thing we did with this whole 1/2 A0 thing up there. Because if it's 1.67%, it's 0.0167 A0 equals A0 e to the 0.000121 t. So the A0s cancel out. So I get 0.0167 equals e to the 0.000121 t. I could change this to log form, so that's log 0.0167 equals negative 0.000121 t. And then I'll just simply divide out both sides by that negative value. So I get the natural log of 0.0167 divided by negative 0.000121. And this tree is really, really, really old, because if I do this number, I get 33,821, and remember that's in years. But it kind of makes sense because it takes so long for the amount to be cut in half, its half-life. So you keep cutting in half, it takes a long time for these things to decay. So hopefully this is helpful. This gives you a pretty good idea of how to set up some exponential growth and decay problems.